You clicked on this video because you suspect your build pipeline is lying to you. You have seen the same code compile successfully today, only to fail mysteriously tomorrow without a single line of code changing. This is not a coincidence or bad luck. It is a fundamental flaw in how most teams approach software delivery. By the end of this explanation, you will understand how to guarantee that the binary running in production is mathematically identical to the one you tested in staging. Here is the hard truth that keeps senior engineers awake at night. A Git commit does not guarantee the binary you deploy today is the same one that breaks production tomorrow. We operate under the illusion that source code is the only variable that matters. We assume that if the code has not changed, the output must be identical. This assumption is dangerously wrong. The reality is that standard build workflows are riddled with hidden drift. Non-deterministic factors like random seeds, build timestamps, and file system ordering create a scenario where identical source code yields different binary hashes every single time you run the build. Consider the typical development environment. You run a build on your local machine. The compiler grabs files from the disk. The order in which it reads those files depends on the underlying operating system. It might read a file named alpha first, or it might read beta first. This ordering is not guaranteed to be consistent across different machines or even different runs on the same machine. If your build process embeds a sorted list of files into the final binary and the sorting order changes, the resulting binary changes. This is not a bug in your code. It is a feature of the chaotic nature of standard file systems. Now consider the security implications of this drift. Many modern languages and frameworks use random seeds to mitigate certain types of attacks. For example, Rust uses random seeds for hash collision denial of service mitigation. This is a vital security feature. It makes your application harder to crash. But this same feature actively undermines reproducibility. If the build process injects a random number into the binary to secure it, the binary will have a different hash every time it is built. You are trading long-term supply chain integrity for immediate security hardening. You cannot verify if a binary was tampered with, if the legitimate build process itself changes the binary every time. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a critical failure mode known as silent drift. You might have a bug in your code that is fixed in a pull request. You run the build, it passes, and you deploy it. A week later, you run the same build again. The binary is different, not because of a code change, but because the build environment shifted. Maybe a dependency was updated, or the file system ordering changed. Now you have a binary that behaves differently than the one you tested. You have no way to know this happened unless you enforce strict reproducibility. Without it, you are flying blind in your own deployment pipeline. The only way to distinguish between a bug introduced by a developer and a supply chain compromise is to force the build to be bit-for-bit identical. If you change the source code and the binary hash changes, that is expected. If you do not change the source code and the binary hash changes, then something is wrong. Either the build environment was altered or the binary was tampered with. Reproducibility transforms your build system from a black box into a transparent trust anchor. It allows you to verify that the artifact running in production is the exact same artifact that passed quality assurance. This brings us to the biggest barrier to adoption. It is not that the concept is too complex, it is that the engineering effort required to achieve it is immense. Most teams avoid this because they are used to the "it works on my machine" mentality. They build on their local development environments, which are inherently non-deterministic. To achieve reproducibility, you must decouple the build process from the host operating system state. You must move from building on your machine to building in a locked-down, immutable container. This requires a complete architectural shift. You cannot just add a flag to your compiler. You need to ensure that every single tool, every dependency, and every timestamp is controlled and predictable. Think of it like baking a cake. If you bake a cake in a kitchen where the oven temperature fluctuates, the ingredients are measured by eye, and you add a random pinch of salt every time, you will never get the same cake twice. Reproducible builds are about creating a controlled environment where the oven temperature is fixed, the ingredients are measured precisely, and the recipe is followed exactly every single time. The Debian project has shown that this is possible. They have achieved high levels of reproducibility across their entire ecosystem. But the cost is high. It requires rewriting build scripts, fixing timestamps, and ensuring consistent file ordering. Some engineers argue that the trade-off is not worth it. They point to the complexity of migrating legacy toolchains. They say that fixing the ISO generation in systems like LinuxKit is too difficult. They worry that the time spent achieving reproducibility could be spent building new features. This is a short-sighted view. The cost of a supply chain compromise is far higher than the cost of refactoring a build pipeline. When a compromised binary masquerades as a legitimate build, you have no way to detect it. You might deploy a backdoor that has been in your production environment for months before anyone notices. There is a critical knowledge gap in our industry regarding the specific quantitative impact of this drift. We focus heavily on theoretical supply chain risks, but we lack empirical benchmarks linking non-reproducible builds to specific operational outages. We do not have data on how many production failures are caused by silent drift, but the anecdotal evidence is overwhelming. Engineers who have implemented reproducible builds report a dramatic reduction in unexplainable bugs. They can now trace every change in a binary back to a specific change in the source code or the build environment. This shifts the role of the engineer from a code implementer to a system integrity guardian. You are not just writing code. You are building the trust infrastructure for your entire organization. When you architect a reproducible build pipeline, you are solving a fundamental trust problem in the software supply chain. You are guaranteeing that the artifact running in production is mathematically identical to the one that passed quality assurance. This is the only way to close the gap between your Git commit and your production build. It is the only way to ensure that when something breaks, you know exactly why. The path forward is clear. You must stop accepting non-deterministic builds as normal. You must embrace the complexity of immutable build environments. You must demand that your tools produce bit-for-bit identical outputs. This is not just a best practice. It is a necessity for any team that takes security and reliability seriously. The future of software integrity depends on it. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.